Observe this runner. He is running on a straight path and at constant velocity. Neither the direction in which he is running nor the magnitude of velocity are changing. What if he was running on a circular path? When running on a circular path, the runner can keep running at a constant rate. But the direction of his movement changes continuously as he stays within the circular path. This is known as uniform circular motion. Let us learn more about it here. If a body moves on a circular path at the same pace, but constantly changes direction, then that body is said to be in uniform circular motion. The velocity of such a body is not constant because it is changing direction. Velocity is a vector unit having both magnitude and direction. Now look at this boy going round and round. The tip of his extended hand is describing a virtual circle. The center of this circle is the center of the merry-go-round. The radius for this circle is the length from the center to the tip of the boy's finger. As you can see, the boy is going around at a uniform rate. The only change is in the direction. Because of this, the velocity at which the boy is going around is not constant. If we know the radius r and the time taken t to complete one rotation, then we can calculate the distance that the boy's finger covers per unit of time. This distance will be the circumference of the circle, whose radius is r. Circumference is calculated by the formula 2 pi r. If we know the time taken to complete one round, then we can calculate the boy's velocity by using this formula. The Earth revolving around the Sun and the Moon revolving around the Earth are other examples of uniform circular motion. In uniform circular motion, the magnitude of velocity remains constant. What changes is the direction, as the object tries to remain in its circular path. When such an object accelerates, then that acceleration is directed towards the center of the circle. This acceleration is known as centripetal acceleration. In Latin, centripetal means seeking the center. Centripetal acceleration is calculated using this formula. As the direction of centripetal acceleration is along the radius, it is also known as radial acceleration. Can you imagine what would happen if this centripetal acceleration suddenly stopped? Inertia takes over and the stone will continue to travel straight.
Bye-bye. Bye-bye.
Centripetal acceleration is as much fun as it is physics. Let us see how. Do you remember how you felt when you sat on the merry-go-round? What happens when the merry-go-round starts and gathers speed? You are thrown outwards and you feel that you might be flung away. What do you do when this happens? You swing your body inwards to stay in the circle. Can you guess what's behind this fun? the physics of motion. More accurately, centripetal acceleration, centrifugal force and centripetal force. The Ferris wheel, the merry-go-round and other such amusement park rides make use of uniform circular motion. Let us see how. When the merry-go-round starts and gathers speed, its fixed framework starts to seek the center. The bucket in which you are sitting and you tend to continue in a straight line due to inertia. This pushing away from the center feeling due to inertia is known as centrifugal force. You have to throw your body inwards to stay in the circle. This is the centripetal force. In the case of the bucket seat, the centripetal force is applied along the line that attaches the bucket to the rotating circle. As the merry-go-round goes faster, the greater is the centripetal acceleration. When that happens, the more you are thrown outwards. The more you are thrown outwards, the greater force you have to apply to stay in the circle.